make some additional research on practical applications.
Okay, I'm back and we can start the conference. So welcome everyone. This is the John Chappell Natural Philosophy Society. Today is February 15th, 2020. So welcome everyone here to the live room. We have 5 participants. And if you would like to join the conference, you need to go to our live conference link. Let's see, where's our live conference link? Yeah, this one here. So if you would like to speak, you can go to our live naturalphilosophy.org link. We can only take a maximum of 6 people participating live. So if you are in the live room and you do not wish to speak, or you want to let someone else speak, and we are at the maximum of 6, then please go to one of our watching links in YouTube. Let's see here, and where's that? Let's see here, where's our watch only links here?
A minor thing, Franklin, is that in your email where it said we're live now, you have this URL down at the bottom, which is correct, but where you have a little banner which says click here to join, it doesn't give that link. It gives a link to the home page of the CNPS. So I think that's slightly incorrect.
Oh, is that confusing? Let's see here. Looks like I don't have my banner for the watch here. Let's see here. Okay, well, in any case, that's the etiquette here. So, but otherwise, if you are in the live room, I will put you up on the screen, and you can feel free to talk. Now, let's see. I gotta hide this other banner here. Why is it I can't even find it? Yeah, that one. Okay, so let's get started here. So this morning, I thought we would discuss a topic that's been going around in the emails, which is the nature of the electromagnetic wave. Now let's see here. Let me bring up the wiki on this. Because there's always this picture of, let's see here, blah, blah, blah. Electromagnetic wave. Okay, there's a good explanation. That's electromagnetic wave. So I'm going to share my screen. Okay. Click on that, share. All right. So this is the conventional mainstream explanation of electromagnetic radiation, which includes light, radio waves, microwaves, gamma rays. So, and the classical picture of the electromagnetic wave is this one you see here, where we have a combination of magnetic and electric fields, which are at right angles to each other, and they appear to be in phase, right? So this is the standard view of how light travels. So first of all, I want to ask you guys, do you have any particular opinions about whether this is the right, whether this is physically correct, actually, which is, I should say. So I want to get, before we start talking about this, whether anybody has any opinions as to whether this really happens. I mean, certainly mainstream thinks it happens. My own opinion is I don't think it happens, but I just want to know what other people think.
There was some controversy among us some time ago, Franklin, that excuse me, perhaps the electric and magnetic fields should not be in phase because, you know, one entails the time variation of the other, and that's reciprocal. But I think the error in that reasoning is that it's not actually the one field which is proportional to the time variation of the other, which would indicate that they're sort of 90 degrees out of phase. But it's actually the curl of one. It's the circulation or the rotation of one, which is proportional to the time variation. So I probably disagree with you. I don't have any problem with the basis of that diagram. It would be something that I would use myself.
I do have problems with that diagram and concepts on several layers. One is I'm not seeing how you have, for example, energy conservation along that wave. Because if you take the square of E and the square of H and you add them together, divide by half, whatever, however you calculate the energy, that goes to 0 along that wave. So you don't have at points along that progression, the energy fluctuates from a max value to a 0 value. And that's a problem for me. Another issue, as I've mentioned, I'm reading Jeff Amenko's work, and he says Maxwell's equations are not causal. And to have them causal, an effect causing a field propagation, for example, he uses time retardation. And when you have time retardation, he shows that a changing electric field does not cause a changing magnetic field, and a changing magnetic field does not cause a change in electric field. What you have instead are the charges, charge bodies, current density, charge density. They change, and they are the source, and they cause a change in electric field and a changing magnetic field at the same time, and they just happen to propagate together. So it looks like changing electric field, changing magnetic field cause each other, but they really don't. It is the sources that are causing the changing fields.
You mean sources as meaning,
charge
actual
bodies.
electric
Charges.
actual charges.
Right.
So that Maxwell's equations exist in the presence of, say, actual electrons.
So the description of that picture that you were showing, where people start saying, at some point that it's not showing the sources of that field in that picture that you were showing, and people often interpret it as, well, there's a change in an electric field causing at that point a changing magnetic field. And Jeff Amenko is in his analysis would say that's not correct. You'd have to go back to the charges, the charge bodies, and those charge bodies may generate an electric field and a magnetic field at the same time, which then happen to travel together, but one is not causing the other. You have to go back to the charges themselves. Anyway, that's just throw that out.
So, are you saying that that it can happen, or I'm still not quite sure I understand the nature of your argument there?
Well, I'm trying to relay what I'm getting from reading Jeff Amenko's work, and how it pertains to this picture that you are showing, and the interpretation often presented with this kind of picture is that you have a changing E vector, I guess in blue, and that is causing a changing B vector in that, I don't know, what is a beige color. And Jeff Amenko would, from what I'm reading of his in his textbooks, he would say, no, that's not a correct interpretation. You'd have to go back to the actual charges.
So that would mean like, you could have something that looked like, let's say you had a charge at the origin there, at the XY there. So you could have a changing electric field, and it might cause a changing magnetic field in what I think is called like the local field, and that, that charge influence would drop off as 1 over r squared, right? So any such influence would also drop off as 1 over r squared away from the actual charge. So what would be wrong with this picture, even if this picture is possible, is that it should be dropping off 1 over r squared in magnitude. I would say at least. I mean, would you agree with that?
That may be hard to picture, but yes. And another thing that this picture doesn't show is a longitudinal electric field component, or a Coulomb field component. So if you actually do have a source charge, it is radiating, and not radiating, but the field is radially from that charge. If you move that charge along the x-axis and then move it back to from the origin in the plus x-axis direction, and then move it in the minus x-axis direction, in other words, oscillated along the line, you are going to have a changing Coulomb field, longitudinal Coulomb field, which is not pictured here at all. So there's another component here, which I think is missing from this picture.
Well, as you bring that up, I mean, I'm thinking that, okay, there is a longitudinal component in here, but it's like pointing straight up and down along the x and y axis. So the only way to produce this would be to like have a flat conductor. And what you're doing is that you have to charge up that flat conductor. So if you charge up a flat conductor, you would get like these blue arrows that are pointing straight up, right? If you have a flat bar. And then you would have to, this bar would have to move along the z-axis, and it would have to be charged up to like a higher voltage and then a lower voltage. So you say you would go from 0 to 5 volts. So you'd have to have this bar that's moving, that's changing from 0 to 5 volts, and then from 0 to negative 5 volts. And then this is what this picture is actually saying, I think, right? That's the only way you can generate this orthogonal, with the arrows pointing that way. Because in general, electric fields, like if you have a point charge, it just shows a point with all the arrows pointing outwards, right? That's what you would get from a circular charge. The only way you could get like this kind of straight up linear pointing arrows is if you had a flat surface that the electric field is coming out of, such that the vectors are all pointing straight, perpendicular to the plane of the emitting thing. And also the same thing for the magnetic field. You would somehow have a magnet that's rectangular, which is actually increasing in magnitude, and it would have to be going from north to south to north to south, I think is what this picture is actually trying to tell you. So I find that all kind of hard to believe. So, but how about maybe James? Do you have anything to add? Have you ever thought about this particular question? And I see you're muted, so unmute yourself. Yeah, there you go.
Hello. Since I was asked, point one, everyone's talking about two fields there, and but no one's talking about what those fields are. And since that the model in the diagram that you're showing is using continuous space-time math, modeling every single point, presumably whatever physical object in that volume of space that is where the field is, has a field encoding device. This field encoding device would have to have a huge database to collect information from other sites that's arriving at that point, and it would have to have a infinitely small supercomputer to do the calculations. In other words, this is why I reject continuous space-time math, because it basically invokes miracles. And I think science should be done without miracles. In my model, if you take the spot unit, there are briefly two types of bits, M and L, which have charge and directional attributes respectively. If you string a bunch of spot units together with the unconditional bit operation, the bits will move in the direction of the L bit. And so you're going to have ML, and then the next spot unit, the L goes to M, and then it could go to, within that spot unit, the M goes to L, and so forth and so on. Now, the M bit has the attribute of electric potential, and that gives you the oscillating wave at this very most microscopic level possible, as far as I know. The L bit has the attribute of acting as a magnetic potential, and they are 90 degrees off in their actions. Okay,
So that gives you
without
that gives
explaining
you a
all this in
method.
great detail, the fundamental unconditional bit motion along what I call a channel, a string of spot units, each one containing an M and an L bit, gives you the picture that you're showing at that microscopic level. So presumably the aggregate effect of millions or zillions of these gives you the macroscopic concept shown in your diagram. Point, stop.
Well, I think that would help explain, say, what the electric field is or the magnetic. You're saying there has to be something in space to represent that thing, and also that.
Well, you can invoke magic, which is what everybody using continuous space-time math does, and they basically ignore the fact. They just say, "Well, the field is there at every point." That's what their math says. Unfortunately,
well, I think physically that's true.
Advanced matrix, vector, and differential equations seem to skip over the fact that if all of this is to be done physically at every single point, you're talking about whatever physical mechanisms are there must be infinitely small. In other words, you're talking about the kind of miracle that you will not, of making something from nothing, which you won't even find in the Bible. Okay, like the making a whole bunch of I don't know the miracles in the Bible. It seems I recall something about making a whole bunch of fish out of nothing for the people to eat on the beach or something.
Let there be. Right?
That is more plausible than what physicists talking about fields at every single point are saying. So what the miracles that the physicists require using continuous space-time math without full quantization, which is the route I've taken, basically requires miracles, and miracles so astounding they would not even be accepted in a theology school.
Say, James,
Yeah.
I had a question about your, what I would call perhaps a lattice model, when you're saying these bit operations and the movement of a bit from one place to another. Is it
Gee,
like
it sounds like you're an expert in binary mechanics. Wonderful. Keep going.
I'm trying to read. But if it's a square lattice, then wouldn't the propagation in one direction along an axis be different than the proper propagation speed or time diagonally at 45 degrees? Because you can't go 45 degrees. It's a taxi cab kind of.
That's exactly right. It's sort of like going from one apartment to another in New York City.
Yeah, but wouldn't that show up in experiments?
On the horizontal plane, you can go up so many blocks, X, go over so many blocks, Y, but then you have to go up to the right floor, and that's your Z. So it's true. Light does not propagate. That's one of the myths in continuous space-time theory, that light propagates along a line at any arbitrary angle.
But
it does not.
Would the speed of light be measurably different at 0 degrees versus 45 degrees?
Macroscopically, no.
Well, that's
I'm writing a paper right now where I'm testing the symmetry of injecting quanta in one side of a simulated cube of space and having sensors for arrival of quanta at the other side. And I know the width of the cube, so I have my length constant. And the number of simulator ticks, each simulator tick being the implementation of each of the 4-bit operations for time development and binary mechanics. And guess what? We get exactly what, in both directions, we get exactly the light speed, which is the bit velocity, which is the length constant divided by the time constant. That's bit velocity. And there are only 2 velocities, that velocity and no movement of a quantum in a time interval. There's only 2 possible velocities. And so anything in between that is an aggregate or a statistical aggregate, okay? And what I'm finding is that the light speed is, just as I've said many times, is bit velocity divided by pi. So in bit velocity units, light speed is 1 over pi, exactly. Which seems to imply that what is pi? That's going to be half the circumference of a circle. So if you can, to address the point about any arbitrary angle, really the light arriving, the quanta arriving at the destination point, the average is going to be pi, 1 over pi. In other words, bit velocity divided by pi, because the average, if by chance some of them arrive faster, that would be inside this circle. If some are arriving slower, they would be going around, you know, a longer path, okay? But anyway, that addresses that question. So you can see that bit velocity, which is just simply the length constant divided by the time constant, because it's postulated that a single quanta can move in one time interval, the time constant, no more than the length constant, L. So that defines your maximum velocity, which I call bit velocity. Light velocity is 1 over pi. I don't know whether I'm answering that question, but at any arbitrary angle, you're going to find the 1 over pi value at a more macroscopic level. Okay, because microscopically, any quanta only moves 1 distance L or none in a time tick T. So, you know, when you're talking about any arbitrary angle, you're talking about a macroscopic measurement involving probably trillions or gazillions of these microscopic events that get you the measurement that you're writing down. By the way, C, the vacuum light speed, is an unexplained observation. It is wrongly called a fundamental constant in your textbooks. It's usually Appendix A in Physics 101 textbook. Pick up any one of them. It's right there, Appendix A. And there's, you know, electron rest mass, Planck's constant. All of these are unexplained data. They're not fundamental constants at all. I've derived all of these values from what I call the primary constants, just to use a different label. A word is a label. I'm using the word primary as a label to distinguish the primary constants for mass, length, and time, to distinguish them from the unexplained data, so-called fundamental constants. Well, I've rambled on here maybe too long, and I may or may not have addressed. I need a graph to show, you know, any arbitrary point to any. I do have an illustration that I've made to show this point, but I haven't published it yet. So sorry, Bob, if I don't fully address what you were saying, because I don't think I have
that's fine.
that illustration.
Okay, you can wait then.
I see Stoyan had a comment. He said he would like to tell his opinion. I'd like to see what he says about that wave picture.
Yeah.
Please.
Okay, my opinion. Initially, the vector that you show, the propagation of light, vector of electrical and magnetic field, it is completely correct. But as said James Heaney, the problem is that all this physics and theoretical physics is based on mathematical constructs. And behind this mathematical construct should be physical reality. And this is neglected because it is ignored the existence of ether. The model of ether that was tested 120 years ago is not what is the real ether. Ether is not a fluid. It is a specific lattice structure that have defined everything: the speed of light, the magnetic field, the electrical field, the propagation of Newtonian gravity. In fact, my theory does all this I investigated 25 years ago, and 20 years ago I published my theory. Here even a page where I explain the propagation of light. It is particle, it is wave, but it is specific wave that rotates, and also it shows that, you know, the photons that's emitted from 1,000 and million years, they preserve exactly their energy. No fraction of the energy is lost. The theoretical physics today doesn't explain this. And but in fact, using the correct concept of the ether, I call the cosmic lattice. I elaborated very detailed model. All this become reasonable, logical, explained. And one essential is true is that between this, as I say, cosmic lattice, these nodes, in fact, the light propagates from one node to the nearby node by the specific time that defines the velocity of light, the velocity of light of vacuum. But it defines also the velocity of light in the optical, in the glass, everything. So all this I developed in my theory 20 years ago, and everything become logically. I call my theory supergravitation unified theory. Why supergravitation? Because it appears the forces that hold this cosmic lattice nodes, the forces between them inverse proportional to the cube of distance, not to the square of distance like the gravity of Newton. And in fact, there is a specifics that these forces, they depends also of how close to this cosmic lattice nodes. So they keep in a particular distance automatically. And in this way, everything become physically and logically explainable. No need to get some presumption of the speed of light and to define like a postulate. It's not a postulate.
But fundamentally,
yeah.
So are you saying that, you know, you don't have a problem with the EM wave picture, but that the problem is that there's no physical mechanism, there's no particularly an ether behind it? Is that your?
Yeah, it is. My concept is like an ether concept, but it has this model has not been investigated never in the history of physics. And in fact, the electrical and magnetic vector really rotates because the propagation from one node to another, the nodes are not rectangular. They have built some kind of rods, and these rods point at each other like a diamond atom. So when investigated the propagation, it appears that there is slight rotation from one node to another. And that's why the electrical and magnetic vectors rotated.
Well, I know that they rotate in, say, circular polarization pictures. That's another even more complicated picture.
No, they rotate not only the circular polarization. They rotate all the time.
All the time.
Circular polarization is different. In fact, the polarization is different because in the polarization, the dimension of the electrical and magnetical vectors become different. In the simple way, this is a elliptical polarization. But this elliptical polarization, if rotating, it becomes like a circular polarization.
Well, one of the questions that, if you believe in this, is, you know, there's this electric field, and where does that electric field come from if it doesn't come from a charge?
Yeah. Electrical field, in fact, is there is another issue also. The elementary particles are not point-like, like considered. They are made by the helical structures, and these structures, in fact, have a helicity that they modulate the cosmic lattice, in my case, the ether around them, and this modulation causes a specific vibrations. They have very high frequency vibrations of the cosmic lattice nodes. So the electrical field makes specific vibration with very high frequency. And this, the vector of the vibration, it becomes a little bit like an ellipse that points the direction of the electrical field. But the magnetic field is different. In the magnetic field, the vibration of the cosmic lattice nodes, they always vibrate, become synchronized in one circle. You know that the magnetic lines, the permanent magnet, the magnets are always circular. And this circle, the vibrations are synchronized by the phase, like oscillators. If oscillators are very close, they are synchronized by phase. In the magnetic field, this becomes the closed circle synchronization. And in fact, this closed circle synchronization has its own energy. If you interrupt this, this energy is dissipated different way.
All right. So now currently we are at our maximum 6 people on the live stream, but actually there are 8 people in the live room. So as I said, as a courtesy, if you would like to speak, please stay in the live room. But if you do not wish to speak, please go to one of our watching links in YouTube so that someone else can be. But I see Jim is here. Jim, did you have any comments about whether the electromagnetic wave is a real thing? Did you have any comments about that, Jim?
Well, can you hear me?
Yeah, we can hear you. A little bit muffled, though, so if you can get closer to your microphone, that would be better. Betsy, can you hear us?
Well, you have to point out that
Go ahead.
The wave equations for electromagnetic waves are for free space where there are no charges necessarily.
Well, I've always tried to point that out. That's kind of one of the...
the simple derivation of the electromagnetic waves, essentially the E field and the B field are derived separately.
Yeah, that's true. I mean, the two problems...
phase between them is not clear to me.
Yeah, there's a lot. All those topics were touched upon in the emails today. I mean, well, going this week. So certainly the phase is in contention. It's like some people feel that the phase must be 90 degrees out of phase because even in the equations that show there's relationship between magnetic and electric fields, they should be clearly like a following thing. So the time varying magnetic field should create the time varying electric field and must be out of phase. But the conventional picture that I had shown shows them actually in phase. So, and people have been arguing about, whether it's in phase or out of phase, or whether Maxwell made a mistake about that. And the other point that was being made is that, free space doesn't have any charges, and all of the Maxwell's equations are couched in the realm of there being, say, actual charges, currents, and wires. And none of those things exist out in free space, right? So,
well, those are the sources.
Yeah, there has to be a source. If there's a magnetic field, there has to be a source. But out in the middle of space, there doesn't appear to be any source. Or like what I was trying to say is that if there was a source, it would have to drop off 1 over r squared, and therefore the radio wave would drop off very quickly.
The equation, Maxwell's equations of any point in space where there are no sources for a wave should still show the difference in phase of the B field versus E field. So, yeah, I'd say that they're out of phase even in free space for a wave.
All right. Now we do have 19 people watching us on the YouTube, and they have some comments here. And let's see here. So we have Harry, who's on YouTube, commenting. And he says to me, seems to me that the ability to send EM waves through space is a miracle. So physics proves miracles are possible. And so, well, I mean, maybe it is, it's miraculous.
Sounds like another adherent of binary mechanics.
Well, I suppose it's a miracle if you truly don't understand what happens in between, because we have a transmitter, we have a receiver, we've been using those for like 100 years, and certainly it works, right? But if we go through like all the emails, people are throwing up all these equations and things like that, and I'm saying things like, well, the EM wave can't travel because there's no connected charges or things else. So it would seemingly be a miracle under current understanding here. But so Kurt brings up this concept of self-sustaining EM waves. And I think that's an important aspect to think about, because we have free space, right? There's, as we mentioned, there's no magnets out there, and as far as we know, no charges either. And even if those charges were to exist, they would have to be this funny, like, magnet that gets stronger and weaker. And theoretically, the self-sustaining happens because we have the magnetic field, and the time-varying magnetic field is supposed to create electric field, and then the time-varying electric field is supposed to create a time-varying magnetic field. So that is kind of the nature of what they're saying is self-sustaining, right? So even though this is like disembodied electric field, right? It's theoretically coming from this magnetic field out in the middle of nowhere, right? But yet that is supposed to be the self-sustaining part. And that's where the whole phase thing comes into matter, and what Bob was saying, that if they're in phase, if the electric field is going to its maximum and the magnetic field is going to the maximum, and then they go to their minimum, then at some point there's zero, right? There's no electric field, there is no magnetic field. So how can then a magnetic field and electric field sprout out of nothing, right? And that's why some people think that must be.
Well, it doesn't. I mean, that's the empty space model, Frank. The empty space model I've debunked. Actually, empty space is teeming with energy quanta in my recent paper, Vacuum Composition. And
Well,
what
it
are those
could.
quanta? Whether the M type, which carry the attribute of electric charge, and the L type, which carry the attribute of a magnetic potential. So there are charges and potentials virtually everywhere. The normal situation in the universe, even in deep outer space, is that the volume is teeming with energy quanta. About 21% of the bit loci in the lattice have a quanta in them. That's teeming with quanta. Empty space is a pure fiction. And that's why people are going around in circles with
and on the
continuous
previous
space-time
comment,
math.
I would say, I would modify it by saying that if there were no ether or medium for transmission, well, then EM transmission would be a miracle. That's what I would modify it.
I agree with Ian.
Yeah, so maybe
Because
maybe
there is
Harry
no
does
empty
need to
space.
recognize.
The curl shows that the. Why do you say that the fact that the Maxwell's equations have a curl related to the time derivative?
Was this my earlier point,
that
Jim? Yeah, I was just trying to.
E and M waves vectors would be in phase.
Yeah, quite so. I mean, if you have a simple relationship where you have one variable which is related to the time derivative of another variable, take a sinusoidal type variation, and conversely, well then effectively you have sort of one value is real and the other value is imaginary, so it's 90 degrees out of phase. But the conventional description is that they're in phase. But I maintain that simple, calculation showing one to be real and one to be imaginary, and therefore being pi over 2 out of phase, is incorrect, because it's not one value, say the E or the H field, which is sort of proportional to the time variation of the other. It's the curl of one, which is proportional to the time variation of the other. It's circulation. Now, I consider it a bit philosophical as to say, what causes it or whether it's.
But doesn't the curl just change the direction?
Well, one would have to do the mathematics on that, but to me that would indicate that the simple explanation that they must be out of phase is too simplistic. It's not based on one actual value related to, say, I omega, the other value. It's the curl of it which is actually related to that. I don't know if you, Jim.
We've got another comment from Kurt Renshaw. Now he's talking about
space. At any point in space, as the time changes.
Sorry, do you, Jim, think that the E and H fields in an electromagnetic wave are out of phase? What is your opinion? Or do you think they are in phase?
Or do you think they exist at all?
At any particular point in space, as time advances, you would apply Maxwell's equations at that point, and that would mean that they were out of phase.
So you don't accept my explanation, therefore. I'm sort of
matters. It just changes the direction.
But out of phase, I would think, right? That's Ian. That's your point that you think they should be out of phase.
No, I'm saying they should be in phase, and that is in accordance with Maxwell's equations. And I've given a sort of simple explanation, which, perhaps Jim isn't accepting, and I might have to look into a bit more detail, to try to clarify this matter, just to ensure that it is correct.
Okay, so let's see. Let's go on to this comment here. So who was talking about grid orientation? Was that you, James, with binary mechanics? I'm not quite sure.
I don't know
what this is about.
I don't know. Apparently, there is a grid orientation, and if you just look up the word anisotropy, there are so many of them listed. I'm sort of amazed that with a fixed grid orientation in my simulations, it's just an arbitrary choice in the simulation, to represent the data on a computer program, that there is so much symmetry, even though the grid orientation is fixed. Okay, but the fact that there are so many anisotropies out there, which is lack of symmetry for those who are not familiar with that term, is amazing, and is quite compatible with binary mechanic thought.
All right, now we got another comment here from Stefan, who says we use Maxwell's theory for technological applications, so this debate is solved long time ago. Okay, so certainly we use those to, say, design electric generators sorts. Although I'm not, 100% sure what are the direct technological applications, or what the direct technological application for the EM wave specifically is for. It's probably something that Harry Ricker would know more, but I imagine it's useful for designing, say, radio antennas. I don't think Maxwell's equations would have any applicability to lasers. Would you? And if so, how? Because a laser is just it's just saying that it's coherent light, right? So that's an EM wave, and I don't know that anything about that has anything to do with specifically time varying electric or magnetic waves, other than the waves have to all be in phase, I guess. But if you're just talking about waves, then that just has to do with wave characteristics, and not that it's built out of electric or magnetic fields, I would think. But if you guys have any comments, could Maxwell's theories be wrong? Well, I don't think the equations are wrong. I mean, they're just the equations. They can't be wrong in the sense that they are empirical equations. They certainly represent what happens to real wires and currents and fields and things like that. So clearly that's okay. But what I think has gone wrong here is this. We got a lot of noise here. Is this concept of the electromagnetic wave? So at some point, science, you had to go back and to the point where people like Maxwell were trying to figure out, what is this electric light thing or this radio thing that we see? Even back then, they may have thought that those two things may have been completely different. That things like radio waves and light waves, those didn't have to be the same thing. We currently think they're the same thing, but if you go back, we have to ask the question, what is this thing? It's like the analogy would be before we knew what DNA was, right? If you ever looked into the history of DNA, it seems so obvious to us now that it's this ladder type twisted thing, and that's DNA. But it took years and years and years and years for people to screw around with it long enough to actually come up with something that actually worked, right? The same thing with light is that, they just messed around with it until they came up with this picture of this varying electric and magnetic fields, and everyone seems to have accepted it. And but the reason is, why? And do we use that specifically? Someone's got a lot of noise here. Do we use that specifically in the design of anything, technological? So I'm thinking, well, maybe not. I mean, one of the key evidences for the electromagnetic wave, say, is polarization, right? Because polarization has to catch one of these, say, electric fields, right? So if you have an electric grid, you have a grid of wires, you send a radio wave through it, it only induces an electric current in only, say, one direction, right? So there are those who would say that because the radio wave can induce the electric field, that there must be at least an electric field present, right? Or that if you put electricity in the transmitter and you get electricity out the receiver, then the thing that must be going through space is electricity, right? Is another way of thinking about it. Although I've argued that, you can say the same thing about sound waves, that, it is the thing that's going through space, electricity, right? Because I use a speaker to generate a sound. It goes through space and it's received by a microphone and comes out as electricity. Does that mean that my voice is transmitted by electricity? And I would argue the answer is no. Your sound is transmitted by a compression of air waves that were sent from the speaker, received by the microphone, and converted into electricity. And electricity had nothing to do with what was going on in between there. So I don't know that.
If I may add a comment here that may be relevant, and I'd like to get the reaction of the others. The comment is, dear friends, that well, I've been in an email conversation with someone that I won't name now, but it's a frequent participant in these discussions here, just out of a courtesy, unless he gives permission to mention his name. But he's doing a lot of calculations. So we're talking about classical equations like Maxwell's equations, and what practical uses do they have, for example, to calculate things. I pointed out to this person, this person was using the so-called fundamental constants, which I call unexplained observations, like light speed, electron rest mass, et cetera, Planck's constant, alpha, and so on. I pointed out that these are not independent variables, and when he plugs these items into his equations to calculate something, he's going to get huge errors, possibly, because the input parameters that he's using are not independent, and he's not accounting for that fact. It's very, very common in the literature to see alpha is equal to, let's take the Bohr magneton. It's a combination of the speed, like you can look that up and you'll see it can be expressed in terms of the reduced Planck's constant, electron rest mass, and the speed of light. So clearly these values are not independent. All of these so-called fundamental constants depend upon the others. So there's a smaller number of truly independent constants at a more fundamental level than what is listed in Appendix A of Physics 101 as fundamental constants. And by the way, this is a blooper beyond belief. Appendix A should be titled Unexplained Data. Not only unexplained data, but perhaps the greatest body of unexplained data in physics in the last century. Stop.
All right, let's continue on with our comments here. So we have Harry saying, electric field is produced by magnetism. That is done in electric generators. Well, I would have to directly disagree with that. If I have a time-varying magnetic field, what that is called is induction in an electric generator. What you're doing is that the time-varying magnetic field, the time-varying magnetic field produces an EMF, an electromotive force, which means it pushes electrons. It doesn't produce and say a static electric field like a charge would, right? See, this is the main problem that I understand induction. Now, I could have this wrong, but in my understanding of Maxwell's equations, is that what we have here is an induction law that says that you have a time-varying magnetic field. You put charges in the presence of that time-varying magnetic field. You get forces acting on the charges, which causes them to move in a particular direction, which generates a current. And a current is different from an electric field, which is the thing that would be perhaps produced by a Van de Graaff generator. Van de Graaff generator produces an electric field, like a negative, specifically electric field. But I think magnetism by itself does not. I mean, that was one of the arguments going on in the email thread. I think Akimbo was trying to say that there is a wave, but it's purely, say, magnetic, right? Although I'm not exactly sure that was the case. He was trying to do away with the people, or at least people are claiming he is trying to do away with the electric component of the EM wave, which I'm still not quite sure whether he was trying to do that. But my claim was that time-varying magnetic fields do not generate, say, radio waves. And they in early radio, they did try and do this. It's easy to create a time-varying magnetic wave. You just wrap a wire around an iron core and you vary the voltage, and that creates a time-varying magnetic field. But the thing is that it would only have a close field effect. I mean, this is what the difference between close field, that which is, let's say, you can detect the presence of magnetic field with a compass, and as you move the compass away, you'll see that magnetic field drop off rather rapidly, right? And if you try to make a radio transmitter out of such a magnetic transmitter, it'll work, but only for a couple of feet. And this is what they use for, say, they currently use this for the wireless transmission of electricity, right? So like between your iPhone and your inductive charger, that's what's being used there, that they're sending a time-varying magnetic field, and it's acting like a very large transformer, right? But those are not radio waves, right? So you can create all the time-varying magnetic fields you want, but they'll never generate a radio wave. And I think that would be a specific prediction of this EM wave equation, that if it's possible for there to be a self-sustaining magnetic electric wave thing, that you should be able to just start it off by a time-varying magnetic field, and the electric field should arise according to the equations, and your transformer should be an excellent radio transmitter. But it's not. It is totally not a good transmitter. So it would fail that hypothesis, right? If you have a theory, it makes predictions, and if you try and test those predictions and they fail, then the theory itself fails. Now, another major point that was going on in these emails, and I kept on trying to drive to the point that the actual electric and magnetic fields have never actually been experimentally measured, right? Now, this is a big surprise, right? Now, finally, David said, yeah, we've never done it, right? You can't measure the time-varying electric field, like if you take an electroprobe, which we do have, or a squid sensor, and you set up a standing rate wave, and you can do that, say, in a microwave. Microwave sets up a beautiful standing wave. In fact, if you put a candy bar in a microwave, and don't rotate it, you can actually see the waves in the troughs, because it will melt the candy bar only in those specific spots, because it produces such a nice standing wave. And you can actually measure the speed of light by seeing where it did the melt points. But instead of putting in a candy bar, you could easily put a magnetic sensor, like a magnetic squid sensor, or an electric sensor, and you should be able to move that along, say, okay, there's the bigger magnetic field, there's a smaller magnetic field. There's a bigger electric field. But curiously enough, this has never, ever been done, right? Never. So everyone
Well,
believes.
Hertz did that very experiment. He measured the nodal points in a standing wave, a reflected standing wave. That's how he basically made his measurements.
Well, yeah, I mean, that's exactly what I just explained with the microwave, that you can see the nodes, right? You can
Right.
definitely measure the wave length, right? But what no one's done is actually measure the time-varying magnetic field that's supposed to be there, right? If we're saying that the electromagnetic wave looks like that picture I showed you in Wikipedia, you know, definitely you've got two vectors there. You've got an electric field vector and you've got a magnetic field vector. Both of those have magnitude and direction.
But you don't have an electric field and a magnetic field. You have an electromagnetic field. They're just different properties of the same field.
No, I would
of the
not
same-
think so. I mean, we definitely have different kinds of things to measure the magnetic field.
Well, you're not understanding what an electromagnetic wave or a transverse wave implies, really. Because if you have a transverse wave, you cannot separate the vertical activity from the horizontal activity in a solid media or a continuous medium.
Why not?
Because it's all bound together. It's like if you were to take your example that you use is like a waving string for a transverse wave, right? That's what you
Some
like to
people
use.
like to do that.
Okay, that's what you've done before. You say you have to have a media to carry the wave, and you have a transverse. So if you, instead of just taking a single line of string to put your transverse wave on, you take a sheet or a blanket or whatever, something flat and long, and you just kind of lay it out with a little bit of tension on it. And you take it and you flip one edge of it up in the center of that one edge. And you have then somebody's, it's being stretched. So that will create a wave within that surface. If it goes up, if you go up and down, and you'll be able to see that wave move across that surface towards the other side, and it will, as it goes up and down, that would be the electric motion. Okay, the electric wave would be the vertical portion of it. But as it goes up, simultaneously, either side of the media or the blanket will be pulled inwards from both sides. So you have an inward tension on the sides created by the upward and downward motion vertically. And so that would be your magnetic from the sides and your electric from the vertical. And they're in phase, they're moving together as a wave. Now you have to extend that then into a three-dimensional media, because if you have a shear wave like that moving in a three-dimensional media, you won't have that surface anymore. What you'll have, let me see.
Well, I think you lost me on the magnetic thing. Like, I can understand you got a bed sheet and you go like this, and you can see the wave
Just use one hand,
from one
okay.
side to the other. I understand that, right?
Okay.
So that's one aspect. And then after that, you lost me.
Okay. So you're moving both hands to begin with. So you're trying to flip the whole bed sheet. Just move one hand, okay? Because you're
One hand. If I just flip a corner.
It's not a corner. Just do it in the middle, okay? You've got the four corners are tied out.
Flip it in the middle.
Okay, it's an infinite length of sheet, okay? And you flip it on edge, and you see a pulse, not a linear wave across, but there'll just be a pulse moving through it, right?
Well, no, if it's a sheet, I mean, I think maybe it's easier can we move over to like a wave pool? Because I understand how wave pools work. We can all imagine how those work. Right, you can dip like a little rod in it.
No, we can't move to a wave pool. We have to deal with a tension surface.
Yeah, well, a wave pool is a tension surface. That's perfectly
okay.
good
Well, we've
tension
got
surface.
the whole media. Okay, there's a pulse moving out from it. It's not like the whole edge of the sheet is changing right at once. You're only moving a portion of the sheet in the middle. Correct?
Well, are we talking about like dropping a bowling ball on a sheet kind of thing?
If you do that, you've got a radial wave going outwards from the center, right? It's circular, spherical.
Yeah, you would certainly have a
so we're
circular wave.
So we're talking about just flipping up one edge of the sheet, and the wave will then move outwards. And in this case, it will spread, and it will spread because there's friction and stuff in material. But
well, what I understand is if you flip it from one end, you're going to get a radial wave, right?
Let's just put it at the starting. If you pull it up, okay, if you simply pull up the edge, what happens to
the whole edge or just a piece of it?
Just pull up the center of the edge, okay? Now that's your vertical change in the tension of there's tension going forwards away from you, but there's also tension going outwards in either direction, left or right from where you flipped it, correct?
Well, that's what we call about a radial wave. If you have a sheet and you only flip like the middle.
The tension going outwards is going upwards only because you're flipping it up. Okay, if you flip it up and down. Okay, if you're flipping
if I have a sheet, right,
yeah,
like this,
yeah,
and I can do one of two things. Now I can try and flip it like from one end like that, I guess.
Okay.
Or I could go like like this and try to flip the whole thing.
No, now you've got now you've got a lateral wave. But if you just flip, if the sheet extends out forever, okay.
But if I just go like or like I flip a corner here, like that. That's going to always create a radial circular kind of wave.
Let me put this way. Let's do it this way. Put 4 people in the corners of a sheet and stretch it. Okay.
Okay, got that.
Okay, you flip the sheet upwards along one in the center of one edge. The 2 people.
How do I do that?
Okay, a blanket. Take a blanket.
I got. Yeah.
They have 4 people hold it. 4 people hold it in the corner. Okay, you get in the middle of one of the edges and flip it up.
Okay, that'll still create a radial.
Okay, so what happens to the person to the left and right of you? What happens to them? They
have to come in a little bit. Yes.
There you go.
In,
okay,
yes.
That's the magnetic. The vertical's tension is the electric. So they're coming in together. That's the magnetic. And the up and down is and moving forward is the electrical. So
I think I finally got you there. Okay, so you're saying
so it's an electromagnetic wave. You cannot have one without the other in a solid. Correct?
Well, certainly you can have an electric field without a magnetic field.
No, you can't.
Sure, you can. I can have a Van de Graaff generator. I can generate a massive negative field, and I can move a compass around it, and there's no magnetic field around it whatsoever.
But
zero.
But
no, it's zero. It's zero.
There are.
Similarly, I can have a static magnet.
Wait a minute.
And I can measure no electric field around it. That's one of the mysteries of magnets.
The mystery is the fact that what happens is it's an electrical charge has both magnetic and electrical characteristics within its structure. How that
no.
Okay, all right, we're done.
See, now the thing is that magnetic fields tend to only exist in the presence of moving electric charges. This is what we know physically.
Okay.
If you have electric charge, static, then physically we know by all equations, zero magnetic field.
All right.
And then the equations say if you take moving electric charge and you move it, that in itself generates the magnetic field.
Here on Earth, all charges are moving.
Okay, wait a second.
With regard to whatever
I just told you.
Background.
I just told you that an electron has an electromagnetic field. The electron, if it's moved, can change its geometry, the wave geometry that defines it, and can then the magnetic portion of it will emerge depending on the geometry. If you take a wave that the one I just described to you, the up and down wave, and you run it in a circle around a circle where it's catching its own tail, you still have the 2 people on the sides will be pulled inwards, but you won't observe the wave going forwards because it's now going around in a circle. So the electric portion may be hidden, but the magnetic portion is visible. And so it's all about the wave geometry and how you put the waves together, whether you'll see the electric characteristic or the magnetic characteristic predominantly interacting with your environment. They are always both there. It's just that the geometry of the waves, how they're moving and how they're put together and how they're interacting with other waves, that the time determines whether you see a magnetic or electrical characteristic of interaction. There.
Well,
So-
I would just have to say that,
So a transverse wave will always have the pulling in from the sides and the up and down for going forward. You cannot have a transverse wave without those characteristics. And you can, however, hide one characteristic or the other more predominantly by how you move it. And you also said that, a magnetic field can't transmit long distances. A magnetic field that's generated by a coil is a very complex structure that structure cannot persist for a long distance, but an electromagnetic wave can persist across the universe, because a transverse wave will always carry that inward pulling force from the sides and the up and down force with it. You cannot separate the two.
Well, I think I understand your concept about, that your magnetic and your electric fields are, I don't know, like pulling forces, although I would probably completely disagree with that. I mean, I could see your physical picture and all, but I don't know that the electric field is some kind of pulling, really. I mean, because the electric field has to be represented by a vector, which is a direction representing the north and the south, and by a magnitude saying how strong that is, right?
Okay, so
Now,
we've got the up and down. We've got the up and down, and the wave is traveling forward. So it's.
And
right.
I would also say
So
that
you got the vector direction of it. It's constantly changing, and it's moving forward in a way away from the source that caused the stress in the first place. It's moving from a stressed region to a less stressed region, and that's because the less stressed region can more easily propagate the waves. So the waves continue to move forward into a region where there is no disturbance, so that because that's where the tension is most consistent and it can move that way. So waves keep on moving for that reason. And so, and we're only talking about like a string so far, and we're talking about waves in a surface so far, but in reality, we have a three-dimensional field, a three-dimensional media that's a tensionable media. So we also have to consider that when this wave moves up and down like this, we're also going to have, there's going to be more media up here that's going to be stressed and relaxed and down here. So you're also going to have, in addition to this wave going this way, you're going to have all additional waves that are going to have to go up and down, and which are going to be your longitudinal waves that are going in parallel with that. You see, that makes sense. In a solid media, you don't have a surface. So your media itself is going up and is being compressed and rarefied this way, while your waves are moving this way. So now you've got to go move into a tensionable three-dimensional media. And that's why you can put something blocking a wave here, blocking the wave, but because the wave is dimensional this way too, it'll go around it, just like a wave in the ocean will go around a pier, and it'll reconstruct itself when it gets around it. So a light wave isn't just a line that the light is traveling on. It also extends above and below that. That's why the slit experiment works, because the wave is actually going through the slits and interfering, and it gets to the other side and comes back together. It's not just. So I'm going way too deep here, but my point was that an electromagnetic wave is that you cannot separate electric and magnetic fields. They are really just a description, a property of a single wave. the electromagnetic wave. And again, how they what property is predominant is dependent on the wave shape, and you can get an electric charge is predominantly electric because the wave is basically captive about a point and actually circulating about that point, and is exposing only the up and down section of it, and the sideways, the lateral section where the pulling in of the sheets is not exposed. And it's more than just circulating around the point, it's actually processing around the point. Because if it was simply if it's simply circulating, then you have a magnet. Because with the circulation, you then have a polarity that you can determine, just like looking at the front of a clock or the back of a clock. You know you have a polarity there. It looks totally different, circulating left or it's circulating right. That makes a magnet. But if it's processing, constantly processing around in multiple directions simultaneous, and it's doing this so fast because it's moving at the speed of light at this little infinitely small dot, we perceive it as being strictly a continuous electric characteristic. But in actuality, it's a wave that's just changing so fast. It's like looking at a propeller. It looks solid, but it's really not. It's a wave moving. It's a propeller moving. And the same thing is true of an electrical charge. It appears to be continuously the same from all directions, but it's because it's rotating so fast or processing so fast around itself. All we see is the electrical characteristic that makes it look solid.
Okay. All right. Well, thank you, Cornelius, for that explanation. Let's go on with our comments here. So we have some more comments here. So Harry Ricker says that he's pretty sure they're real since he uses them every day, and certainly he does as a radio expert. Harry uses, he's certainly using something, although I think the bone of contention here is whether it is actually an electromagnetic wave, meaning that it contains electric and magnetic components. So, I mean, but what would be the alternative to that, right? What if the thing that the radio transmitter is transmitting, the thing that the receiver is receiving, is not consistent of electric and magnetic fields as in the Wikipedia, then, what is it, right? So, but as a materialist, my point has been that it's got to be just an ordinary type compression wave similar to sound. That is the alternative here. And then that's what I would continue to argue. My point, my opinion, if anyone's interested in my opinion, is that there is no electric and there is no magnetic field in a misnomered, mislabeled electromagnetic waves. I'll just call that a radio wave, okay? Radio wave, I don't believe has any actual electric or magnetic fields present in free space as it travels, would be my claim. Now, I'm not a mathematician. When I see all that math and Maxwell's equations, it just makes my eyes roll, and I really don't understand it. And, that is kind of a problem because I really should, but I'm just not a math person, right? So, and that may be an advantage or disadvantage, right? It may be there's this in the emails this question about, well, you've been overeducated, right? And therefore, if you have been indoctrinated with, say, the wrong theories since birth, it's going to be much harder for you to let that go, right? And so I challenge people because quite clearly, people are agreeing with me that has never actually been measured. There's no measurable H, there's no measurable E in a traveling radio wave as it travels through free space. I mean, it's just never been done, right?
Yeah.
But yet people believe that this is exactly what happens, right?
Well, like we just pointed out, though, it's not one or the other. It's an electromagnetic wave. Can I ask on a sideline? I am on StreamYard, and I've heard people say, if you want to talk, raise your flag. I don't see any flag on my desktop. Plus, I have the live chat comments showing up on the side. I don't see any way to enter live chat comments in StreamYard. I have to actually go to YouTube and enter my comments to show up in StreamYard. So does anybody have any issues like that, or Or am I?
Well, when you're in the live room, unfortunately, there is no raise your hand thing. So
Okay.
what I'm doing is that if you're in the live room, I'll always add you to the stream.
Okay.
And it'll be up to you to mute or unmute your microphone so that you can be heard.
Okay, I just asking
Generally
that
speaking.
because I was asking that because I've heard people say before that, you know, that just raise your flag and I'll let you talk, and that I didn't see a flag. What about the live comments section? I can't write in the live comments. I see no place to write live comments. I actually have to go to YouTube and write my comments to see them show up in StreamYard.
Well, what we have is if you're in the live room, we have a thing called private chat.
Okay, I see
And
that.
you can put things in there, but unfortunately, I have to still moderate those, and I still have to go over and actually see those. So
Well,
that's what I'm doing. Is that if you type in something in the private chat, I'll get like a little notification that someone's put something there.
Well, see, I see that.
But unfortunately, I have to then copy it and then put it into the public comments in order for you guys to see it.
Into the live comments?
Yeah, so it is actually easier for you if you just want to make a comment like that to put it in YouTube. I think so.
Okay.
That's one of the weird things about and limitations of StreamYard.
So it's not just something that I'm experiencing. I think that
No.
So there's no way to, if I put something in the private chat, you will see it, but nobody else will?
Yeah, I will see it, but no one else except people in the live room will see it.
So what I see in live comments is all stuff that you've had to put over there?
No, what you're seeing, like this comment here from Harry, those are coming from YouTube or Facebook that I can easily put up because I see those comments as well, but I can just click on them. I can hide or show them, right?
Okay.
So
I didn't know if everybody else was having
that.
Okay, I didn't know if everybody else was having that understanding or not. Yeah, it is kind of cumbersome that way then. Thank you.
Yeah, it is kind of cumbersome that way. So, but like Harry made this comment here about, we have a well-developed theory and they produce E and H fields in phase, or so they say. I mean, Harry keeps on pointing out that those are the facts of EM theory, right?
Well,
those are the facts. The facts of the EM theory is that they are in phase. That's the fact.
This blanket scenario we just spoke about, they are in phase. When you're talking about in phase and out of phase, the only place I see in phase and out of phase really being of any significance is when you're talking about electrical charges moving through wires or because the current. So when you're talking about an actual physical current where electrical charges, electrons are moving through wires, the electron's motion, the center of the electron, because an electron is again a wave pattern, but we don't worry about that. Just call it a ping pong ball if you want. The electron can be compressed and rarefied as it's being forced to move along the wire. If you want to look at it as kind of a compressible thing, which is way off, then as you compress it, it can change shapes, which will be the wave, and that'll cause the next one to move, and its wave will move forward. But the actual delay of the center of the electron, the mass of the electron moving from location to location is being delayed from the force being applied to it. And that's where you get a phase delay, is when you actually have an electron or a mass being accelerated or decelerated by an electromagnetic force. That's where phase comes into play. As far as being an electromagnetic wave being transferred through space, it's like the blanket scenario. If I go up, as soon as I start going up, the people on the sides of the blanket start feeling it being pulled inwards. So it's not a delay in that sense. And the only thing that it's the right angle situation, which if you want to call that. And sometimes I think people get that confused that the phase angle, the angle of the delay within a cycle of an electricity for a cyclic electricity has a phase angle of 0, 1, 2, 3, and have 90 degrees, as opposed to a 90-degree right angle that the physical horizontal versus vertical electromagnetic characteristics of a wave are. But as far as being transmitted through the atmosphere and through a open space where there are no electrons, if that's how your model is, and that's how mine is, there are no electrons, it's just tension, then there is no such thing as a phase relationship because there's nothing to be moving. There's just so that's how I look at the phase relationship. And I think that's what Harry is saying. They're in phase. Well, this is true for an electromagnetic wave moving through space. The phase and shape, the only time you deal with phase is when you actually have a particular electron that's being accelerated or decelerating. That can be
I mean,
delayed.
you're saying that they have to be in phase because they're like always in phase, right? So there's no.
Yeah, because there's no physical mass that can be delayed, as opposed to when there's a physical mass of an electron and you're pushing on it, there can be a delay between the push being put on it and it's beginning to move. And then when you push it back in the opposite direction in a cyclical manner, it can take time for it to slow down, turn around, and come back the other way. It's like accelerating a car. You can put the force on it early. You can put the force on the car, but then it's going to pick up speed, more speed, more speed. Now you're going 10 miles an hour, and you put a backwards force on it. You change the force here, but the car is still going forward, and you reach a point finally where the car now stops and goes backwards. That delay between changing the direction of the force and actually changing the direction of motion is the phase delay. And so you have to have actually a physical object that you're relating the phase to, the force versus the motion, directional motion of it.
Okay. Well, let's see. Harry's got a few more comments here. So he's talking about curl equations that don't apply in free space. So he seems to think that if they don't, then that solves a problem. Because he says that curl equations apply to the physics of capacitors and inductors, not free space. Now, I'm not 100% sure what all these curl equations are.
Can I speak to the curl equation a bit?
Okay, sure. What is he talking about?
Okay, talking about, let's go back to the blanket situation where you have a curl equation. As I pull up the edge of the blanket, I will have a slope going forwards that basically goes down towards the norm of the blanket. And if I bring it up and down, I will have the slope changing. I mean, turn the camera on. I'll have the slope change. The slope changing. I'm doing this backwards, and it's messing my mind up. So the slope is the curl down as it slopes up or down. That's changing the curl. The angle of the wave is the change in the curl, as opposed to the in and out of the sides. So you have a curl this direction, and you have an in and out tension this direction. And so in an electromagnetic wave, it's actually a curl and an anti-curl thing that's going on. As opposed to an electron, you have a curl where the wave is just continuously moving around in a circle. Actually, if it's moving around in a circle, then it's a magnetic field. If it's moving around processing, then it's an electric or a magnetic force. And if it's moving around processing, but anyway, that's where I get the curl. The curl is actually the tilt, the changing in an angle of the vector, because that's what a curl is the rate of change of an angle.
Yeah, it's the rate of change of an angle, although I'm not quite sure what. So that explains what curl is, but I'm not sure that explains why that solves the problem. Now here's another interesting comment we have here from Alistair here. I like this quote here. Quote is, what do you call a wave without a medium? Mass. Oh, I love that comment, because I think that is so true, that if you have a wave and you're not saying that it comprised of any actual medium, then what you have there is just a set of equations, right? And it's just totally math. And that's what we seem to have with Maxwell's equations, is that it's a pile of math. One of the interesting parts of the posts that we've gotten is that we have the original paper from Maxwell about when he actually derived this thing, right? So there's a link here, and you could go to this link. Let's see. Let me see if I can make that link here. Let's go ahead and put that link up. Okay, so this is an actual link to Maxwell's paper, when he came up with this whole idea that the EM wave is actually made out of the electric and magnetic fields here. So let me go ahead and share some of that with you here. Let's take a look at that. And through the miracle of the internet, anything that we ever wanted to know about any particular topic is totally at our fingertips. So this is his original theory, electromagnetic theory of light. So at this point, it was just like, unaccepted theory, trying to figure out, how to explain electromagnetic phenomenon by means of mechanical action transmitted from one body to another by means of a medium occupying the space between them. So, that with the start of Maxwell's paper seems to be quite sensible, because he's saying that, okay, we're trying to explain this, and we would like to explain it by a mechanical action transmitted from one body to another. And he calls like the undulatory theory of light, which assumes the existence of a media. And so I think all of that seems to make sense. But as we go on the paper here, we start to get into increasingly complex levels of math here. Until, he starts looking at the independent properties of magnetic and electric fields in here somewhere. Even up to this point, he's still talking about undulations in a non-conducting medium. Let's see here, but at some point he makes the leap that he's calculating an electrical disturbance, right? So somewhere in these pages, he's making the leap from light being like an undulatory phenomenon in a medium to something having to do with plane waves. Until finally, he comes up with this picture, figure 67, which is, the resulting start of what seems to be the electromagnetic wave. So that's kind of the development he has of this entire idea, which we have now accepted wholesale, and this is like, one of the most, commonly unquestioned, accepted theories that electromagnetic waves travel with these perpendicular magnetic and electric fields, like that, even though this electric field and this magnetic field have never actually been experimentally observed. Never. It's never been observed.
Well, there's a couple of comments, if I may. One could fundamentally say that the electric field is just a name, and the magnetic field is just a name. They're names of phenomena which we're experiencing, just as we might say in the acoustic case that strain or stress, they are just names, and inertia is another name. So we're finding effects, and you talk about lack of measurement of these parameters or these quantities. But we can affect. It's a measurable experiment that we can affect the behavior of an electromagnetic wave by applying an external electric field, and similarly we can affect its behavior by applying an external magnetic field. So there is some reality to this, but they are just names. You can say, well, I don't want to call them that. I call them some other name. But we can measure the effects. Now, the other thing with regard to the phase is maybe a simple way of perhaps reducing those Maxwell equations would be something like this, that if you have something like the magnetic field H is equal to H naught times the sine of a quantity which is dependent on the time and the displacement, the place in space. So something like H naught sign into omega t plus kx. Now, it's true that if you partially differentiate that with respect to time, you get a cosine, excuse me, which would be 90 degrees out of phase. So that's true. That's a simplistic way of looking at it, just differentiating. However, if you're looking at the curl, well, the curl is effectively a differentiation in space, as I think Jim said. So if you partially differentiate that, H naught sine omega t plus kx with respect to space, x, you will also get a cosine term. So in other words, the curl term is a cosine term, and the induced electric field by differentiating the magnetic field is also a cosine term. So ergo, they're in phase. So I don't know if that makes sense, but that might be a simple way of explaining that it's not the actual value which is proportional to the differentiation of the other one, but it's the curl, the circulation of that. So I hope that's maybe clarified a little bit.
Okay, we got another interesting comment here. So is a water wave self-sustaining? I would say yes, in fact, it is self-sustaining. I mean, that's an example of a self-sustaining. If I go in a swimming pool and I put my hand in there, and we can see it go from where my hand is to further away. It doesn't last forever, but it's self-sustaining in the sense that we have an elastic substance. When I add energy into that elastic substance, it stores that energy as potential, as like a wave height, and that wave height travels because the elasticity is transferring the energy from place to place. So in that case, you can see that there has to be this concept of elasticity in order for there to be this kind of self-sustaining kind of thing. Maybe that explains, why is it when they say that the E and H wave go to zero, that it then sprouts out of nowhere, because maybe it's put its energy into this elastic substance, which is then giving it back out again, right? That we can't see. I mean, that's always a possibility. But certainly the idea of a self-sustaining wave is not an unusual one, right? Because that's the funny thing about waves, and that they can move from place to place. They don't actually do a net motion of the medium that's involved. But there's something about the kinetic energy of what's in there that is providing this kind of self-sustaining, regenerating thing that keeps the wave alive, I guess.
Yeah, one point about the self-sustaining is, like you did point out, that it does eventually die out, but the reason it dies out is because the tension within the wave gets distributed within the particles that it is moving through as heat and random energy, and it is absorbed. Whereas if you had a continuous medium without particles, there would be no place for that self-sustaining wave to be absorbed. And the only way to absorb those waves would be actually to create a particle or a wave pattern within the media that would then absorb the wave rather than let it pass on in its normal condition. So in that sense, self-sustaining, yes, because it does propagate through additional media, but if the media is absorbing it, then the sustaining part of it deteriorates.
Well, I'm not sure if I really agree with that, because you're saying that you can get around the eventual destruction of the wave by just saying that you've got a medium which is not consistent of parts or something to that effect.
Yeah, therefore light can travel across the universe without being diminished, because it's traveling through a medium that's not particular, that's not absorbing it by each particle it encounters would absorb a little bit of its energy.
Yeah, but that's kind of like, if it's not particulate, then it's, I don't know, solid, right?
Exactly.
And if it's if it's solid, I mean, truly solid, I mean, although all the solids that we know about on the Earth are also particulate. So we're talking about a solid that no one has ever seen.
So if it's truly solid, then the only thing can move through it is waves.
No, if it's truly solid, then nothing would be able to move through it, right? If it contains, that's just my point I gave to you the last email sent to you, that if it contains no parts, then there's no place that you can measure a change. I mean, if it's truly solid, then there's no give to the material that such that you can measure. You know, the wave is there, but it's not here, right?
And
How can you say?
My reply to that was what? My reply to that was, yeah, and you used the word yourself. You can't measure it, because the only way you can measure it is if you recognize how that tension interacts with other patterns of tension. And so in order to have so it is the particulate characteristic that is derived from the tension being amplified, magnified, and focused to a point which makes it look particulate, that is those high tension areas interacting with other high tension areas, or one node interacting with another node, that gives us the ability to measure the amount of tension and the motion of the tension. It's like we can't measure the tension in the surface of the ocean unless we see the waves, or we can't measure the tension in a guitar string unless we create waves in it. And we'll notice that, oh, these waves are moving faster than that waves, even though the same guitar string is made of the same material. This one must be tensioned differently. So it's the interaction of the tension and the velocity with which those waves move through the media that tell us whether there's tension there and how much it is. So it's the tension itself, the clue. It's the tension itself and the density of those tensions.
Well, I mean, that's all perfectly true. You know, I have no problem with that. But, you know, guitar strings are made out of particulate media. And the only way we can tell if there's a tension is because they're made out of particulate media that can be, which actually change in distance, right? That's the only way we can tell there's a tension on them.
But the only reason we have to use a guitar string as an example, as an analogy, is because you can see a guitar string change frequency. You can't see space change frequency until it interacts with a guitar string, or interacts with a tension space. What's happening is the rate at which processes occur is dependent on the degree of tension within the media. The rate at which a guitar string vibrates is dependent on the tension within the guitar string. The rate at which an atom vibrates is dependent upon the tension within the ether.
Let's see. Well, okay. Well, we've got some other. We're getting towards the end of our show here, so I want to get to some of these other comments here. Let's see here. So, but Jim brings up the point is he thought that Maxwell's equations apply everywhere. Now, I'm not an expert in this, you know, even in free space, but, you know, Maxwell's equations have to do with the presence of, say, electrical currents, time-varying electrical currents creating time-varying magnetic currents, or that if you have a charge, you know, it has certain properties. So all of those things have to do with, you know, real charges, real currents, and that's their realm of applicability. So I keep on saying that, well, in free space, you've got none of those things. You've got no charges, you've got no magnets, you've got no currents. It's outside the realm of applicability because, you know, Maxwell's equations got no problem with those things, but those things apply to real charges, real currents, real wires, real magnets, physical things, and in free space, we got none of those things. So I'm saying that this whole, whatever this mess that Maxwell did in his paper, that was a complete no-no, because none of those things can apply in free space. That would be my argument, I would guess. And, you know, so we have some other comments that Maxwell equations has some problems. I don't think there's a problem with that. I think it's the application of those things in places that they don't belong, I guess. So But Binko points out that they're not causal. Maybe that's the problem. He's talking about Maxwell's equations. And how do you go from Maxwell to discrete charged bodies, and discrete charged bodies to Maxwell? I'm not exactly sure what this comment is about, because Maxwell's equations have to do with, say, discrete charged bodies. I guess that would be the relationship here. Unless anyone else has any comments about that. I guess because he's saying Maxwell's system equations has problems doing that. But I'm not sure that that's what they were supposed to be doing anyways. Now, we do have some comments here about the astronomical note, which is that the celestial sky is a projection from the Earth's magnetic field. Well, I'd say that's a very far comment there. Let's see here. And we have a comment from Ed saying that radio, electric, magnetic, light, all different modulations of one thing. Well, I don't know that certainly radio, electric, and light are accepted as all being the different modulations of one thing, but magnetic seems to be, I would say, at least in a different category all of its own, right? And we have a comment from Richard. It says a medium that doesn't exist can't either be compressed or rarefied. And that was kind of my point with Corey, that if you're going to talk about waves, then there must be something physically there that can represent that. Now, typically that's a compression or a rarefication, right? Now, I suppose if you're in a computer, you could represent a wave just, I don't know, mathematically, and that wouldn't have to be a compression or a rarefication. It's just a 0 versus a 1 or something, I suppose.
Or it's a tension relaxation, correct?
Yeah, a tension or a relaxation, like a relaxation or a tension. A tension is a pulling of a physical medium, solid typically, which causes the particulates to come further apart. That's a tension.
Yeah. So if I take a string that's got particles, and I pull on it, then each particle there's a binding energy from particle to particle, atom to atom. And if I make it smaller and smaller so that it's 1 atom thick, there's a tension between those particles, those focal points of energy. What is between those focal points of energy that's pulling them together? Because actually those focal points of energy are focal points of tension. So,
well, they are. I mean, I agree with you totally. But the thing is that
if you go down to the infinite level, the only thing left between them is a tensionable media. Otherwise,
or what's between them is a void. I don't know.
Well, if there's a void, how are you going to create the tension that keeps the string together?
Well, probably because, I mean, there does have to be a medium. But I would say that medium is more easily recognized as being particulate. I mean, between the carbon atoms of the string.
What's between the particulates to pull them together?
Well, between the particulates of the actual medium, then you would have a true void. There's nothing how does that void communicate tension? I have sent you that article about if you can set up waves between two generators that will create a pushing effect, because there's going to be more pushes on the outside than on the inside. That creates an attractive force.
And it's in water, which is a tensionable media. And it's the tension within the media that allows the waves to occur. And it's actually the tension that surrounds the two spheres that causes them to be pulled together, not the pressure or lack of pressure between them.
No, I say it does definitely the pressure. The pressure on the outside greater than the pressure on the inside. There's no tension between the two like experimental balls which are pulsing.
Right.
That's not really the cause.
It's the pilot wave theory, where the two waves are trying to unite with each other and join with each other, because when they are united and joined with each other, the overall tension within the media is relieved. Just like two bubbles on the surface of water have less tension in them than when they're combined than when they're separate. The same thing is true of two spherical wave patterns within the submersed within the water. So it's still all about tension. And you still go back to the fact that if you have a string that's infinitely thin, you have no way that string can be pulled together unless you're saying every particle in the universe has talked to the other particles in the universe and say, we're only going to push in this direction because otherwise the string would be crooked or collapse.
By the way, in that extract from Maxwell's volume 2, if you look at it, you will see that he has a term in there. I think he calls it C, which is the conductivity of the ether. Now, invariably, Maxwell's equations are quoted with that omitted. In other words, C equals 0. So actually, they're quoted very frequently incorrectly. So if you look at the original equations, which you have there, you will see that term C it indicates a dissipation, because there's a term which is proportional to the rate of change of the variable, whether it's the electric or magnetic field, and it's multiplied by that C term. Let me see now. It's
I don't know that I see the C term, but
okay. It's just a bit small, but I think you may have to go back a little. Maybe even another couple of pages. I think it's earlier. No,
because most of this is a
here you
mechanical.
are.
There's a C.
Yeah, that's it there. So if that term were equal to 0, well, then you get the simple wave equation there. You know, K is epsilon naught and so on. The dielectric constant. But C is what I call sigma naught, which is the conductivity of the ether. And it's interesting that Maxwell actually has it here. And he does actually say, well, if you reduce it to 0, you get the simplified result. But that is invariably what is quoted in all the textbooks. You know, it doesn't actually indicate that term is non-zero, and that the current expostulation of Maxwell's equations is really a simplification.
Well, are you saying that if C is 0, then we're just back to regular conventional compression waves?
If C is equal to 0, not only are we back to the simple compression type rarefaction waves, but there's no dissipation. From one end of the universe to the other, this electromagnetic radiation is transmitted without any dissipation. But if C is non-zero, well, then there will be a dissipation. And therefore, you will get, if you what has been called like a sort of a tired light effect, which can account for a redshift in the spectra of distant.
Well, he seems to be saying that C
Or
equals
the
0.
1 over
See?
R squared effect. That the luminosity decreases with distance.
So it's that on top of the luminosity effect, because the luminosity effect is simply, I suppose, that the circumscribing area falls off with the square of the radius, and that's true. It's always going to happen. But this is actually it's a bit like a thermodynamic effect. If you have molecules of the air which are being compressed and rarefied, well, then there'll be a frictional effect, and there'll be a loss of energy because you're heating up the molecules owing to the oscillating behavior, movement of them. Now, in this case, you have an electric and a magnetic field, and you have in the process of the electromagnetic wave being transmitted through the ether, you have a sort of a conductivity, which is sort of a slight heating effect, if you like, of the ether. It's causing the etheric molecules, whatever they may be, to vibrate. So it's quite analogous to the dissipation of heat in an acoustic wave. But it's important.
The terms ether and void have been used. The terms ether and void have been used in the last few minutes And I picking up on what Ian said a while ago about names referring to phenomena. In research methodology textbooks, this is commonly called an operational definition for a name or a concept. Now, what I would like to ask is to those who are using these terms ether and void, to what is the operational definition, which is going to tell me how I could go into my laboratory and get a bottle of ether or get a bottle of void. I'd like to go get a bottle of void in my lab. What do I have to do?
You can't get a bottle of ether, but because a bottle of ether would basically be nothing more than a tensionable media that everything is made out of.
A bottle of ether would be like a bottle of perfect vacuum, I would say. You could get easily make a bottle.
Void doesn't exist because nothing doesn't exist. You know, you can look at it that way. If there's nothing.
Well, I think that you could theoretically make a bottle of void. You'd have to take all of the particles which make up the ether and remove them. Of course, they're being removed against this tremendous pressure. But if you could do so, then you would have something where no radio waves could transmit, no light. It would be like this perfectly black thing or perfectly reflective thing because nothing could penetrate it. But it's in practice could be theoretically created.
A void is simply the ether devoid of any tension anomalies or any tension patterns. Is indistinguishable from one region to the next because the tension is equivalent throughout. It's only when you become where there's an imbalance of tension that you can recognize that there is any difference from one location to the other. And the reason you can recognize there are differences is because of the velocity with which those tension waves move throughout that region. If they move faster, then the region is of higher tension. If they move slower, then the region is of lower tension. You also have a tension curve where the tension isn't linear. So you can actually have a point. You have a stress strain curve in a media. It usually reaches a point of maximum tension, and just near that point of maximum tension, it loses its elasticity. And as you lose elasticity, then you lose the ability to transfer tension. In other words, the tension will slow down. It's at that point of the media that the oscillatory action occurs, and you get waves that form into particle or halide patterns and become focused. You're at the maximum tensile strength because at that point you go from a positive feedback where increased tension causes increased velocity to any additional increase in tension causes a decrease in velocity. So you now have a yin and yang, and you have an oscillation about a point within the tension media that creates a particle, a focused nodal point within the media. So to your point, James, nothing or a void within the ether is a lack of any distortion, any non-symmetry whatsoever within the tension. How much tension there is in the media overall, you cannot tell because you can't. There's like a tree falling in the forest. You have to have a way of distinguishing between them. You have to have at least two different points of tension to be able to determine anything.
Okay, so we have James. You have a couple different answers to what the ether and the void might be. Okay, but we are at the our end of our time here. Thank you for all participating. So just kind of wrap up. So the topic of our discussion is the nature of the EM wave and whether, let's say, this thing actually exists. So we discussed this. We discussed, what does this picture actually supposed to mean? What could it possibly represent? And, it's been argued that, this is supposed to be a self-sustaining thing. So somehow, though, we're talking about, say, self-sustaining waves in water, that there would have to be some kind of medium that's storing the energy, like a tension. And Cornelius has been talking about tensioning waves, and he gave an analogy using a blanket and a sheet and how things are being twisted and turned in different ways as a possible solution. But it was also discussed that this particular picture has never really been experimentally confirmed, which would be my my personal conviction. My personal conviction is that the electromagnetic wave is just an ordinary compression wave. And so we also discussed Maxwell's original paper, which we displayed, where Maxwell does kind of start out that way, and that it's just trying to determine the effects, but somehow comes out with this plane waves with mixed electric and magnetic field kind of thing. I mean, that's the origin, right? So, but that has been a main topic of discussion going on in the email chains. And so if anyone is interested in this humongous long chain about this debate about, is it in phase, is it out of phase, does it just contain magnetic components, does it not exist at all, I can forward that to you. You can send something to franklinhu@yahoo.com, and I can forward like some of those posts to you if you're interested. Or you can see all of these discussions actually. If you go to Google Groups and search for the group NPA Relativity, I cross-post all of these things to that area, so you can go ahead and read those things without actually being involved in them. Because if you get yourself on one of these email lists, it's like a curse, because you get like 20 emails in a day, and you'll waste half an hour just reading through them, right? And then not even have any time replying to them. But if you want to see the discussions, they are there in Google Groups. But that will do it for this week's CNPS Science Chat, and hopefully we'll see you next week. And thanks for everyone who's been tuning in on the live streams. Thank you. Bye-bye.